As you can see, I'm all prepped today. I decided to record using my phone after all. The problem was, the reason why I was using a camera initially is because iPhones have a very narrow field of view, so it doesn't take the whole board into view. So I got that extra lens on top, and now it's wide view again. It's just like a normal camera now. And I also got a mic just so you can hear me okay on the recording. Awesome. Let's get started and see how the recording comes out today. All right, so I heard you guys have a test next Tuesday. Yeah? Chapters 10 through 12, and 13 hasn't been started. Great. That leaves us with plenty of time. We started chapter 12 last time. We're going to finish it up today. And in the remaining time, I'll go over some select topics from the last two chapters, just as a refresher. All right. So last time, we talked about relative rates, right? How to compare the rate of consumption of the reactants to the rate of production of the products, right? That's what we did. Today, we're going to discuss rate laws. Rate laws is different from relative rates that we discussed before, okay? What we discussed before is just how to translate the rates of consumptions and productions of the various species in a chemical reaction. We were comparing rates to rates. Now we're going to compare rates to concentrations. So what this tells you is I have a beaker. I start with a certain molarity of these reactants, and then I let the reaction start. If I know how much reactant, if I know the concentrations of the reactants that I had to begin with, can I predict how fast the reaction is going to proceed just based on initial concentrations? Okay, so that's what rate law is. Rates based on concentrations. And turns out you can do that. And so rate law looks like this. Let's work with an example reaction. Say nitrogen reacts with oxygen or ammonia or hydrogen to form ammonia. Yeah? My reactants here are nitrogen and hydrogen, and so the rate of the reaction will be given by the concentrations of the nitrogen of the concentrations of the reactants, which is nitrogen and hydrogen, raised to some powers, right? So it's raised to some powers, m and n, and then you have an overall constant up front. That's what a rate law is. Remember from last class, square brackets mean, anyone remember? So concentration comes in various forms, right? You have molarity, you have molality, you have mole fraction. Molarity, yeah. Square brackets here in this chapter and for the remainder of chemistry will be molarity, moles per liter. K here is called the rate law constant, not surprising. M and N here are called the order of the reaction with respect to those reactants. So some terminology. M, which is the power of N2, you would say M is the order of the reaction with respect to N2. N is the order of the reaction with respect to H2. What would order of the reaction as a whole be? Yes, M plus N, the sum. So M plus N is order of the reaction as a whole. And individually, it's order of the reaction with respect to that particular reactant. Okay? Great. M and N can be different. They could be some powers, 1, 2, 3, even 0. If M is 2, you would say that the reaction is second order with respect to N2. If N is 0, you would say it's 0th order with respect to H2, and so on. Okay? M and N here reflect the relative sensitivity of the reaction to these two reactants. Not all reactions are equally sensitive to each of the reactants that are present, right? So reactions are sometimes asymmetric. They're very sensitive to the concentration of one reactant, but not very sensitive to the concentration of the other reactant, or may not be sensitive to the concentration of another reactant at all. That's called 0th order reaction. So the sensitivities can vary, and that is reflected in M versus N. Which one's greater? That's the reaction is more sensitive with respect to that reactant. Awesome. So the first thing that we're going to do, the favorite question from this topic is to determine rate law given a bunch of information. Okay? And determining rate law simply means you want to calculate these constants, K, M, and N. That's all. That's what it means to figure out the rate law. Once you figure out your K, M, and N, you're just going to write it like this. Rate equals substitute your K value that you found and substitute the M and N values that you found, and these are just your variables. Okay? We'll go over that with a question now. But remember, what we're trying to do here is find these three constants. We'll always figure out M and N first. First, you figure out the powers, and then lastly, you determine the constant. It makes the math a lot simpler. Okay? It's practical advice. Awesome. Let's get to a question. Can I erase this? Okay. Yes. With respect to, yeah. Common math notation. It's getting hot in here. It's supposed to, I feel like we're complaining now, but come winter, we'll be grateful that this room is warm. Yes. Reaction. Yeah. I'll often abbreviate reaction with RxN. Yeah. All right. Cool. Let's do a question. Determine the rate law for the reaction given the following. So you'll be given the molarities of N2 and H2 and the corresponding rate. Okay. Usually you're given a table like this. Say when this is 0.1 and this is 0.1, you get a rate of 20. Say when this is 0.2 and this is 0.1, you get a rate of 40. And lastly, if this is 0.2 and this is 0.2, you still get a rate of 40. Okay. The units here are, what was the unit of its molarity, right? Big M. Rate is always in units of molars per second, right? How many molarities of the reactant is getting consumed per second? How much molarity of product is getting produced per second, roughly speaking? Okay, molars per second. Awesome. So all we got to do now is to write down the skeletal, the general rate law, which is rate equals K times, our reactants here are N2 and H2, so you're going to put those in molarity parentheses, and it's raised to some powers M and N. And all you do is, for each of these 3 data points, you're going to plug in the information into this. So you get 3 separate equations. How many unknowns do we have total to solve for? 3. And so how many equations would you need? 3. You always need the same amount of equations as the number of variables for there to be a unique solution. Okay. Let's plug in the first line into our equation. Rate is given to be 20. K, concentration of N2 is given to be 0.1 to some power N. Concentration of H2 is also 0.1 to some power N. And repeat for the second and third line. Yeah? We just substituted the values at these 3 different concentration states into our general rate law. Next, we solve for the powers, M and N. Okay? So the trick here is to use 2 equations where the k's cancel. So we're going to divide these equations. That's our rule. Remember, algebra allows you to add equations, subtract equations, multiply equations, and also divide equations, provided that there is no 0 in the denominator. Okay? So division is legal. So we can, here, the most effective thing to do is to do division. We want to choose 2 equations in which one of the reactants has the same molarity, so-called fixing a reactant. So let's fix the first reactant, N2, i.e. select 2 equations in which the molarity of N2 is the same. Let's call this equation 1, 2, and 3. What 2 equations have the same value for the molarity of N2? 2 and 3. Great. So we're going to work with equations 2 and 3, and we're just going to divide them. Whoops. I stole the chalk this morning, so I think this is karma. Okay, let's divide these 2. So the 40s go away, that's 1. K gets canceled by K. And by design, the M variable also gets canceled, right? It's the same thing up and bottom. And what survives here is 0.1 divided by 0.2. They both have the same power N, so I can take it out as a common power. And now all you have to do is to solve for N. What's 0.1 over 0.2? It's 1/2, right? So 1/2 to the N equals 1. If I take the reciprocal of both sides, if I flip both sides, I get 2 to the power of n equals 1 again. Any questions so far? Okay. 2 to what power gives you 1? 0. Anything to the 0th power is 1 except 0. Right? Anything to the 0th power is 1, provided that you're not doing 0 to the 0, because 0 to the 0 is undefined. Aside from that, it works. And so you figure out that n equals 0. Great, you solve for your first variable. If you don't want to do this guessing game, you can do this algebraically. You can solve this like automatically using math. What's one function that brings down the power? Log, right? So take the logarithm of both sides. If you do that, you're going to get log of 1 equals, taking the log of this whole right-hand side, it's going to bring down that n, so it's going to be n times log of 0.1 over 0.2. What's the logarithm of 1? 0. That's something to memorize. Log of 1 is 0. 0 equals, this is some logarithm, it's 1/2. It's some number. This is not 0 for sure. Log only goes to 0 at 1. So if this is non-zero, but the product is 0, divide both sides by log 1/2, what do you get? 0 again. So sometimes if you don't want to guess, just take the logarithm of both sides and solve for the power. It's convenient. Great. Fixing one reactant gave us one of the powers. Now let's fix the other reactant, H2. What two equations do I use this time? First and second, correct. Yep. So let's divide those now. (20 over 40 is 1/2. K's cancel. The 0.1 to the n cancels, but the m survives this time. Taking out the common power of m. (0.1 over 0.2 is 1/2 again. So this is 1/2 equals 1/2 to the power of m. What must m be? 1, right? Or if you don't want to do this, take log of both sides. You see the same thing. M equals 1. Awesome. So we have found our m and n, one variable to go. To solve for k, anybody has any ideas? How would we solve for k now? Yeah.
Just plug in the reactants and the rate for one of the...
Yep. Take any equation, plug in your m and n that you found, and the reactant values for that. Okay. All right, plugging in our information into the first equation, 20 equals 20 times, 20 equals k, 0.1, 0.1. M we've found to be 1, and we've found to be 0. And now all you have is one variable, which is good. Anything to the 0, this becomes 1. That's just 0.1. And so k would be 20 over 0.1, 200. The last step is always very easy. Yeah.
What are the units of K?
What are the units of K? Excellent question. K, rate constant, its units depend on the overall order of the reaction. So let's figure out what the units here would be. Right? So K doesn't have any uniform units. It depends on what M and N are. It actually depends on what M plus N is. So we can figure it out though. Rate, we know, is always molars per second. K has some units. I don't know what it is. I'm just going to put it as K. What are the units of N2? N2 concentration. Molarity, right? Big M. What's the power M? 1. And then again, that's M, concentration. Power N is 0. Solve for K, and that gives you your units. M to the 0, that's 1. M and M cancel. And so for this particular reaction, the units are 1 over second, which is second inverse. So this is going to be 200 second inverse. Okay. Let me actually make up another question based on that question that you asked.
Question.
Yeah.
So the final answer would be like
Oh, yes.
everything plugged in except the.
Yep. Rate equals 200, which is K, concentration of N2 to the power of M, which is 1, concentration of H2 to the power of 0. You may not choose to write H2 there because it's 1. Yeah.
Or it says A equals K and then polarity 0.1. Is that a negative one or a positive one?
Here,
Yeah.
positive 1. Yep. Okay. Yeah. You let me know if it's not recording. Okay. Great. Let me make up another question. A certain reaction has, wait, don't look. I need to make this up. Has 1 over big M squared second as the unit for the rate constant. Determine the overall rate of the reaction. Okay. So in the last question, we had the overall rate of the reaction. Using that, we determined the rate constant's unit. This is the reverse question. Okay. Overall rate is given by what? If your powers are M and N, M plus N. So we need to figure out what M plus N here is. Okay. Rate law looks like this. K, concentration of, let's say our reactants are A and B, doesn't matter. rate here, well, rate always has these units, molars per second, like we discussed. K I have given to you. It's 1 over molars squared seconds. And then I have a molar coming from here, a molar coming from here. So that's molar to the m, molar to the n. How do I combine that? M plus n, molar to the m plus n. Awesome. That's what we need to figure out, the m plus n part. Okay. Seconds cancels on both sides, right? Both in the denominator. And if I bring the molar square up here, I get molar to the power of 3 equals molar to the power of m plus n. From this, can you tell me what m plus n must be? 3, right? Same base on both sides, so the powers must be the same. So m plus n is 3, and so the rate, the overall rate of the reaction is 3. As a fun little exercise on your own time, make up this table. Figure out the units of K for a couple overall rates, 0th order, 1st, 2nd, and that's enough. 0, 1, and 2. On your own time, just figure out what K, the units of K must be. Everyone clear on how to do this? Okay. And I think it is helpful to memorize. Just like keep in mind what the units are. It'll be quicker that way. Cool. All right. Enough rate laws. Now let's focus on something that is derived from the rate law. This is just a continuation of rate law. Integrated rate laws. We're going to use some calculus here. Specifically, do you guys know what the integral of x to the n dx is? A simple integral? How many of you taken calculus before? Okay, so some of you have not. Okay, so when you take the integral of x to the n dx, yeah.
U plus 1 and over
Yeah.
n plus 1.
Yeah, and so it's x to the n plus 1 divided by n plus 1. Integrals also have limits. You integrate from one number to another. Let's call that a. Let's call the lower limit a, upper limit b. And so when you find this, you're going to evaluate it at the limits a and b. I'll tell you what that is. You basically just plug in b for x, minus you plug in a for x, and you subtract. Okay, we'll do something like that. But that's one you need to know, and another one is if you have a single x in the denominator, ln x, yeah, and then you want to go from a to b. Great. Remember, a reaction can be very sensitive on the concentration of a certain reactant, or it can be not sensitive at all. And we said that that reflected on the power that is associated with that reactant. Okay? So let's study 3 cases. One where the power is 0, another one where the power is 1, and the third case where the power is 2. And we're looking at only one reactant at a time. we're used to writing rate law as rate equals K times both A and B, right? Concentration of A and B. But now I ask you to focus only on one of them at a time. So if the reaction is 0th order with respect to, let's say, a reactant A, then its rate law is going to look like this. K times concentration of A to the power of 0. Okay? Great. Recall from last class, or 2 weeks ago, rate for a reactant is related to, it goes like this, right? dA dt. This is what rate is, dA dt. And if it's a reactant, we write negative, and if it's a product, we write positive. Here we'll always use negative because we're dealing with the rate of the reactant, consumption of reactant. And there's also dividing by the overall coefficient for that particular thing. Let's just pretend that it's 1 here. So this is the rate of consumption of A. So I'm just going to replace rate with negative dA dt. What's a to the 0? 1, so that's gone. It's just K. And now this is a common trick that you've seen in calculus, perhaps. You treat this derivative as a fraction and move the dt over. K dt. So far, so good? Let me just make this a little bigger. And I'm also going to move the negative over. So it becomes negative K dt. Okay? And now let's integrate both sides. We start our watch at time equals 0. Okay? So t equals 0. This is the side that's being integrated with respect to time. So the limits here belong to time. We start with time equals 0, and then say we stop at some time t. At time equals 0, let's say that the concentration of A, the molarity of A, was A0. And then at time t, let's just say it's A. Okay? So we're going to integrate this equation and then plug in those limits. It will be easy, I promise. This looks novel. If this looks novel to you, the first and the second will just be repetitions of this. Exactly the same. Okay, cool. Remember, integral and derivative and differential, to be exact, cancel each other. They're opposite functions. So if you take the integral of a differential, you just get back the original variable. So here, the integral cancels with the d, and so you just get a. Let me write this here. You just get a evaluated from these limits. A naught to a equals, k is a constant, negative is a constant, these come out, minus k, integral of dt. What's that? T, right? The integral and the d cancel again. Yep, so that's just t, but you evaluate that from 0 to t. Yeah. Great. Let's plug in molarity of A for molarity of A. That's the same thing. So this is just going to be A. And then subtract the lower limit. Plug it in. So you get A minus A naught equals, if I substitute T, it's just going to be T. If I substitute 0, nothing. And so what's on this side? Negative KT. Because if I substitute 0, there is no term. So there's only the first term from the first part, negative KT. Solve this for A, and you're done.
And this helps us find like the concentration at a specific time.
Hmm?
This helps us find the concentration.
Yeah. Yeah.
This is all for zero, right?
This is, yeah, for a reaction that's 0th order with respect to A. Yeah. This is how the rate of a reactant involved in a reaction whose order is 0, this is how its amount changes with respect to time. Okay? So this is very powerful because it tells you, this is all you need to know. When I started my clock, I had 2 molar concentration. 50 seconds later, what is the concentration? Just plug in the values and you'll find it. So this tells you exactly, this allows you to predict how the concentration of A changes with time as time passes. Okay? And since we integrated to get there, that's why these are integrated rate laws. These are just restatements of rate laws, but integrated in their integrated form. So this tells you what the new concentration is at any given time in the future. Let's do the same thing with first order and second order. Okay, now that we're familiar with how this goes, let's repeat the steps again. So this will be extra practice, basically. So what rate law am I going to start with? Rate equals K. What will be the power of A here? 1. Awesome. So that's just that. I'm just going to write 1. Rate, like we said, is negative dA dt equals Ka. So far, so good. I'm going to move the dt over. So my goal here is to have, I have 2 variables here, right? There's A and there's T. I want on one side all the variables of the same kind, and on the other side the variables of the other kind. So this is separating the 2 variables. Okay? There's an A here and an A here, so I'm going to bring the A down. So dA over A will be equal to, I'm going to bring the negative over K and the dt over, negative K dt. Compare and contrast, they look pretty much the same, right? There's a dA, there's a negative K dt, but there's an extra A because of the power. We had A to the 1 here. Okay, now we integrate. Remember, time goes from 0 when the clock starts to some time t. At time equals 0, concentration is A naught. At some other time, it's A. Good? You know what the right-hand side here is going to be, because it's the same as the other one. Just negative kt, right? Negative comes out, k comes out. Integral of dt is just t. 0 to t, that's t minus 0, just t. So the right-hand side here is no surprise, it's negative kt. Let's look at the left-hand side. What does this remind you of? You have d times a variable, or d of a variable divided by that variable. Oh, I erased it. D of a variable divided by that variable. What did I give you the result of this to be? ln x. Awesome. So this will be ln of A, where we're going from A naught to A, applying the limits. Cool. Let's plug in the limits. ln of a minus, I'm going to plug in a naught, so ln of a naught equals minus kt. And if you solve for a, you're done. Before you solve for a, we can do a nice little mathematical trick here. So if you add two ln's, that's the same as multiplying the two things, right? Remember laws of logarithms? ln x plus y, ln x plus ln y is ln of x times y. And if I have subtraction, that turns into division, x divided by y. So ln a minus ln a naught becomes, it's subtraction, right? So a over a naught, that equals minus kt. My a is trapped inside an ln. How do I free it? What's the opposite function to ln? E. So you e both sides. So a over a naught equals e to the minus kt. And so if I just move the a naught over, I have a equals a naught times e to the minus kt. Good? So the common part, the hard part ended here with integration. This was just rearranging it to solve for a. Fire alarm. I don't know if it's a drill. Are we supposed to leave? Let me check. All right, no, we're fine. Okay, great. Any questions? Yes.
So one time it's going to let you exam, we can use the one.
The final one, yeah, yeah.
We don't have to show the steps.
Nope.
Okay.
I'm just deriving it for you, yeah, because it's fun. Yeah, you're just going to use these last equations, and we'll do questions related to the last equation. But I just wanted to show you how, like, it is straightforward to come up with this. Yeah.
What does first, like I know for the zero order is like concentration at a specific time, but what's the first?
Same thing here. This tells you the concentration at any time in the future, t.
So can't you use the zero one though? Like why do you?
Because it depends on if the reaction, if your preferred reactant is zeroth order or first order or second order with respect to the reaction. Whether it's zeroth, first, or second, that's determined by nature. Yeah, so you can't choose. Yeah. Yeah, they'll specify what order it is. All right, let's finish this off with the last one. And you tell me what to do. Okay, cool. Rate equals, what do I write? K times a to the power of 2. What is rate? Let's bring all the a's on one side. And everything else on the other side. Integrate. Same steps as before. We go from 0 to some time t, from a naught to some concentration a. Great. What's the right-hand side? Negative kt, good. This, remember, this was x to the n plus 1 over n plus 1. A squared in the denominator is a to the negative 2 in the numerator. Yeah? So the answer is going to be, I take my x and I raise it to n plus 1. N here is negative 2 when I bring it up. Negative 2 plus 1 is negative 1 over negative 1. Whole thing going from a to a naught. Let's simplify that. I can take out the negative. A to the power of negative 1 is 1 over a. Going from a naught to a. And on the right hand side, as usual, we have negative kt. The negatives cancel, which is nice. And now let's just plug this in. 1 over a, when I plug in a, minus, when I plug in a naught, it's 1 over a naught, equals kt. Solve for 1 over a. And you're done. So it's the same process over and over again. If you like doing math, try third order at home, and you'll start to see a pattern. And if you really want to generalize it, do it for any nth order, whatever n be. N could be 4, 5, 6, 7, whatever. All you need to know is this up here. That'll work. Great. Awesome. So we have derived our 3 rate laws, which is good. Now let's talk about their graphs real quick. 10:50. Awesome. Okay, for graphs, tell me what the 0th order equation is again, the final thing. Hmm? Yeah. Uh-huh. Minus kt. And what is it here for the first one? Mm-hmm. This we also had in another form, ln a equals ln a naught minus kt, right? This is before I eat both sides. We have something like this. This is first order. And then lastly, we have second order. Which was 1 over a equals 1 over a naught minus kt. This is the equation. This is one of the equations of a straight line, right? If you have a line that crosses the y-axis at a point C and it has a slope m, then that's the equation of the line. Another way to think about this is if you have an equation in this form, then the coefficient of x is the slope and the other number is the y-intercept. Great. Does this look like that? What are our variables here? Let's mark our variables. Let's call this y. If we put this on the y-axis, what's the other variable here? T, right? So this is x. So tell me what the slope would be? Negative k. It's what's multiplying x. So I can rewrite this as negative kt plus a to make it more apparent. That's your slope. And that is your y-intercept. So if I plot a graph, y-axis is a, x-axis is t. Slope is negative k, right? That's a negative number. So our line would be going down. And it's going to start at, what is the y-intercept? A naught. So this is what the graph looks like. And eventually at some time t, it's going to hit the x-axis, and this indicates that the reactant is over. You've used all of it. So the main thing that I want you to remember here is that the graph of A on the y-axis versus t is a straight line. Okay. The other two graphs are weird, and you don't know exactly what the graph looks like, but I'll tell you. If you plotted this for first order, if you had A on the y-axis and t on the x-axis, it would look like this. It's an exponential decay. It keeps decreasing, but it never becomes zero. Here, pretty much the same. So both first and second order look kind of similar. Well, they're pretty much the same. Okay, so it's like an exponential decay in both cases. Both never run out, theoretically speaking. However, we can still get a straight line. This equation looks like a straight line if I treat this whole box as y and this whole box, this as my x. You see? So if I plot, instead of a, if I plot ln of a on the y-axis and t on the x-axis, so tell me what my slope here is for ln a versus t. For this equation, what's my slope? Negative k again, so going down. And what's my y-intercept? Natural log of a naught. So it's going to look something like this. Y-intercept is ln of a naught. Slope is minus k. Same thing here. Okay. Notice the big difference. A versus t is not a straight line. Ln of a versus t is a straight line. Okay, that's the key difference. So okay, last part, second order. A versus t is not a straight line, but let's see if we can hack it. If I take this mess as my y and this t as my x, then what's my slope? I'm going to plot 1 over a here and time on this axis. So what's my slope this time? Still negative k. That's my variable. That's the number multiplying it. So it's going down. And what's the y-intercept? 1 over a naught. Yeah.
Plus KT.
Oh, yes, you're right. It is plus kt. So the slope for the last graph, actually, it's going up. You're right. So it's going up, and it's going to start out here, because that's the y-intercept, and then it's just going to go up. Does this mean that the reactant's concentration is increasing over time? Reactant is supposed to get used up, right? Why do we have a graph going up? Any ideas? If A is going down, what would happen to 1 over A? It will go up, right? That's the solution. Because this is not a graph of A versus T, this is a graph of inverse of A versus T. So this is as expected. Reactant is indeed going down, but since this is a plot of 1 over A goes up. Okay.
I have a question.
Yes.
So since that one's going up when we plot 1 over a, what about a versus t? Would that also still be exponential decay?
Yeah. Not technically exponential decay, but it pretty much looks like an exponential decay.
And it has to look like that.
Yeah. Yeah, so the graph of A versus T for both first and second looks alike. Yeah. But for 0th order, it's nice. It's just straight down. Yeah, so here 1 over A versus T is a straight line. Great. How much time do we have? Okay, great. Let's do some questions. Before we do a question, one last topic. Going back to first order reactions. Notice, first order reactions, the reactant never runs out, technically. So the reaction takes an infinite amount of time to complete. Yeah? So if you ask about what's the life, infinite. Right? In principle, mathematically speaking. So that doesn't tell you anything. But